Hello everyone, this is lecture 12 of course PE 645. In this lecture, we are going to cover the last step of the radiomics workflow, which is explainability. And in the previous lectures, we have covered the other steps, including acquiring the data set, extracting different features, including first order features and second order features, developing the AI model, applying a set of pre-processing techniques such as feature selection and data balancing, and we discussed a set of performance metrics, and we concluded that we need a system with a high performance and explainable. And here in this lecture, we will go through this step. So interpretable and explainable AI, or in short XAI, focus on making machine learning models transparent and trustworthy, especially as AI systems are increasingly deployed in critical areas such as healthcare, finance, and autonomous vehicles. And we need different techniques for explainable AI that aim to clarify the decision-making processes of more complex black box models like deep neural networks and ensemble methods. Some models are explainable or can be understood, such as linear regression, but other models can be treated as black boxes. So we need to deal with these models to explain their decisions. So the aim here, we need to explain how this model got the decision, based on what features, based on what criteria. And when you provide an interpretable AI model or framework, then you are building trust among the stakeholders such as doctors and end users, because this will enable them to comprehend why a model makes specific predictions or decisions. For example, let's say in healthcare, doctors need insights into which patient features led to the diagnosis. So the idea here is simple. We have a certain model, whether we know how it works or it's a black box. It takes some inputs and it produces an output. So we need to add something that can interpret that model. So once it gets the decision, it says, based on what criteria I took the decision, or what features led to that decision. In that case, we will gain an interpretable model alongside a high-performance model, so that we can trust that model and confirm that it's transparent. One of the common frameworks in explainable AI is called SHAP, or Shapley Additive Explanations, and this framework enhances the transparency and interpretability of complex machine learning models. And this framework is based on the concept of cooperative game theory, especially something called the Shapley values. And here, these values fairly distribute the credit for a model's output among the different input features. And the Shapley value, let's say it's phi I for a certain feature I, and we can calculate the phi I or the Shapley value for feature I using this formula. It consists of two parts. The first part, which is here, is called a weighting factor, and it's based on the subset size and the total number of features. And the second part measures something called the marginal contribution of feature I when added to a subset S. And S here refers to subsets of features excluding I. So when you find something like that, this means we have a subset, union subset, so we are merging the two subsets together. So S only means we are dealing with a subset excluding the feature I. Subset union I means the subset including I. And F here is the function. So if we have a subset union I, and we are getting the contribution here, and then we are getting the contribution excluding I, then here we are getting the marginal contribution of feature I, as we are getting two values, one with I and one without I, so subtracting both of them together will get the marginal contribution. And absolute F here means the total number of features. And this partition in the summation means all subsets of the features from F, and the capital F is the all features, and backslash I means excluding the feature I. So here we are getting a subset which is included in the features or the whole feature set, excluding the feature I. So the situation here is simple. We have a summation, and this means we have a loop, and S here means a specific subset in each iteration. So we need to iterate all over the subsets S. So we have different subsets, and this reflects the different combinations of the features, excluding the feature I. And in each iteration, we are calculating the weighting factor, which is here, and the marginal contribution, which is here. There is a factor, a numeric value, and there's also a numeric value, but it's calculated by substituting with the feature subset into our model or function, one with including the feature I and one without the feature I, and getting the margin by subtracting, multiplying both of them together and summing all over different combinations. This will gain the Shapley value by I. And here we will get a Shapley value for a certain feature. And this means what is the contribution of the feature I. To understand that, let's move to an example. We have the formula here. And let's say we have a machine learning model that predicts whether a patient is at risk of heart disease based on 3 different features: age, blood pressure, and cholesterol. And we need to get the Shapley value of the feature age. So the first step, we have I, or the subset I, which is the subset including the feature age. And the number of features, F, or absolute F, is 3, because we have 3 features. And F excluding I here means the other features, which are blood pressure and cholesterol here. So S is included or a part of that. So we need all combinations excluding the age. This means we have an empty subset. We have a subset with only blood pressure. We have a third subset with cholesterol only. And we have a fourth subset or a last subset that includes blood pressure and cholesterol. And in sets, the ordering isn't important. So blood pressure, cholesterol, or cholesterol, blood pressure in a subset are similar. After that, we need to calculate for each subset the corresponding value or the prediction value, and the same by adding the feature I, we need to calculate the contribution or the prediction or the output using the function f. So let's assume that we have predictions of f of s and the prediction of f of s union the subset I. This is here and this is here. And actually we calculate them, or it's calculated through the model. So we have a trained or fit model, and these values will be the output of that model. So let's assume now we got these values from any fit model or trained model. The next step is to substitute. Let's first calculate the marginal contribution by subtracting this value by this value. So 0.5 minus 0.1 is 0.4, 0.7 minus 0.3 is 0.4, and the same for others. Now we got the marginal contribution for all subsets or all combinations. We need to calculate the weighting factor, and this will be the next step. For the first subset, it's empty, so the length of it will be 0. Those are 1, and the last one is 2. Now substitute here. We have the length of the subset f is 3, and here is 3 factorial, because the exclamation mark here means factorial. So 3 factorial is 6, so here is 6, and the factorial of s in the first one will be 0. 3 minus 0 minus 1 will be 2, factorial will be 2, so 2 over 6 will be 1/3. The next one, substitute 1 factorial, 3 minus 1 minus 1 will be 1 factorial, over 3 factorial will be 1 over 6. Substitute in the rest, we will gain the weighting factor in each iteration. Now, multiply the corresponding weighting factors and the marginal contributions. So, multiply 0.4 by 1/3, 0.4 by 1/6, 1 over 6, 0.4 by 1 over 6, 0.3 by 1 over 3, and calculate the overall value. This will be the Shapley value or phi of age, and this value, which is around 0.37, is the contribution of the age to the model's prediction across all possible feature combinations. If we did the same for other features, then we will understand and know the contribution of each feature in a certain decision. Now, it's your turn. Instead of dealing with the age, let's say now we need to deal with the cholesterol. So here are the predictions without the feature cholesterol, and these are the prediction of the different combinations union the cholesterol feature. You can pause the video and test your understanding. As we mentioned, we are dealing with SHAP and the Shapley value, and SHAP also provides something called global and local explanations, and both of them will enable a comprehensive understanding of the machine learning model and the decision-making process. So what is the meaning of both global and local explanations? Global explanations provide an overview of how each feature influences the model's prediction across the entire dataset. Let's say the global explanation might reveal the age, blood pressure, and cholesterol levels are the most influential features among the entire features and the entire records. And inside SHAP, as we are going to see, we can use something called summary plots or bar charts to explain the global explanations. On the other hand, local explanations focus on individual predictions, and this will detail how each feature contributes to a specific outcome. Let's say that the patient's high blood pressure and age increased their risk score, while low cholesterol mitigated it. So, local explanation from the word local means we are dealing with a certain record and a certain outcome, and we need to explain the contribution of each part of the features to that outcome. And the global explanations deals with the entire dataset that can say we have 10 features and these 3 features are the most influential features. So it's simple. SHAP provides the 2 sides, one across the entire dataset and another across each record or each outcome. To use SHAP framework in Python, simply install the package using the pip command pip install SHAP, then bring your fit model, or from the beginning you can train and fit the model on the preprocessed dataset. By all means, at this stage we need a trained model. Then initialize something called the SHAP explainer and apply that on the train and fit model and the data. Then compute SHAP values for the test set to explain the model predictions or your external dataset. And finally, visualize the required plots to gain insights about the data and the corresponding features. So it's simple. After installing and training your model, apply these 3 steps. Create an explainer, create the Shapley values, and create the plots. To understand how to use SHAP with your fit and trained model, you will first need to install SHAP as mentioned, pip install SHAP, and then based on the trained model, we need to import it. If you remember from the previous project, in the previous lecture, we have stored our models in a pickle file. Each configuration or each experiment is stored in a separate pickle file. So simply, based on the best hyperparameters, we can get these hyperparameters from the Optina configurations and then load the corresponding model. How to do so? First, we applied a small update to our machine learning classification version 3 by simply storing the current columns, and these columns are the output after removing the none or empty values from rows and columns, and we need those columns to select the features from the testing dataset and also selected features. These are the output from the feature selection process in case of the feature selection is applied. So this is the update, and after running and training the model, each experiment or each configuration will contain that dictionary as an object stored in a pickle file. So first, we defined which experiment that we need to deal with. So we selected here first order features and we defined the different paths in case we need them. Then we set the Optina best parameters file, and if you remember, we stored it in Optina best parameter as a CSV file in the storage folder, and here we defined the path and loaded it as a data frame. Then we replaced none values with none, because if you remember again that our pattern in storing the files contained none for empty values. So instead of raising an exception during finding the folder, we applied here filna with the non-string. Then we got the record as a dictionary. Now this will be a dictionary that can be printed on the command window, and this dictionary will contain the best hyperparameters, including the model name, the feature selection name, and so on. So here we accessed the different hyperparameters: the model name, scalar name, feature selection technique, data balancing technique, and feature selection ratio. And here we checked if it's not none, get the value, otherwise set it with none, just as a check. Then we defined the pattern, and we followed the pattern similar to the machine learning version 3 or the pattern we used in the previous lecture, because this pattern will be the pattern of the model stored in a pickle file. So here we loaded the pickle file, we got the objects, and from the objects now we can access the different things such as current column, the scalar, feature selector, and so on. Before that, we loaded the dataset because we will apply feature selection and normalization on the data. We here loaded the test dataset. Then we selected XY separately and used the current columns, which was a result from the dropna in the training process, to get the X after filtration. If there is a scaling or normalization, apply it and convert it to a data frame. If there is also a feature selection, apply it also and convert it back to a data frame and use the selected features as a header. And what we are doing now until this moment is preparing the data so that it looks similar to our experiment. Simply, what we did is we loaded the best hyperparameters, and based on these hyperparameters, we loaded the corresponding model stored in a pickle file, and the model or the object stored in the pickle file are used to unify the pattern or the theme of the data. Here we loaded the data set, the testing data set, and applied scaling and feature selection. You may wonder, why didn't we apply data balancing technique? If you remember, we mentioned that we apply data balancing techniques on the training subset and we avoid that on testing subset, because in testing subset we don't need any redundancy or unreal data. So now the X here is a data frame which is ready now to be applied to our model. We got the model which was also stored in the objects dictionary, and we used the explainer. If you remember here, we mentioned that we need to load what we have stored or fed or prepared. Then we need to initialize an explainer using the model, which is fed or trained, and the corresponding data. And here we are. We created an explainer using the prediction function from the model and the data. Now we have the explainer. What's after? We will compute the corresponding SHAP values for the testing set to explain the model prediction. So as you see here, the next step is to compute the different SHAP values for the test subset. So now we have the SHAP values. Based on these SHAP values, we can plot the different figures, which is the last step, and the step to gain insights about the data and the corresponding features. Here, it's a step to get the corresponding predictions, aiming to know if the presented figure for the local explanations, aiming to know if the predictions are similar to the actual for the figure, which is presenting the local explanation for a specific instance. Here, we are selecting a random instance to explain. So each time you run the experiment or the code, it will get a random instance, and this will be for the local explanations for a specific instance. And we are focusing on explaining the hyperplasia, which is set to be the first class 0. So you are setting the index of the class here. And then we determine the number of records to visualize, 150, and you can change that number according to your data set. The more you increase, the more time it will take to visualize. And here we need the top 5 features, and all of those configurations will be used during the plotting. Here we visualize the waterfall plot using the waterfall function, and it accepts the instance by simply getting the SHAP values, and SHAP values here is the result of the explanation. We accessed the instance at random index, and here we are getting the top 5 features from the beginning to the number of features, which is 5. And here we used show equals false because by default it will display and open a figure in front of you. Instead, we need to store it. So here we set it to false, and then we stored it in a PNG file so that we can update the title and anything that we need to update. Here we set the title to include the index of the random instance, the true label, and the predicted label. And here comes the rule of doing that. We call the predictions, aiming to highlight that in the title for each figure. So the waterfall plot explains the prediction for a specific instance by simply breaking down the contribution of each feature. And this figure shows how the SHAP values or the feature contributions accumulate to produce a final prediction. Here is the waterfall plot, and we applied that on the first order features experiment. The x-axis here represents the SHAP value contribution, and the y-axis is the features. As you see, we selected the top 5 features. Each bar of those corresponds to the feature's contribution to the prediction, and the features are ordered by their magnitude of impact on the prediction, from the top to the bottom. And the base value is the average model output over the training dataset, is shown at the bottom here, and the final prediction is shown at the top here. So we have the base value. If it's above that, it will be targeted to a specific class, otherwise it will be targeted to another class. And the title here, as you see, the true label is hyperplasia and the predicted label is hyperplasia, so the figure is correct and we can interpret it. If you find blue, this means that the feature value is contributing negatively to the prediction, pushing it lower, and this will be to the left direction with the negative sign. And if you see red, this means that the feature is contributing positively to the prediction, pushing it higher to the positive. So this is our base value. If it's lower than that, it's predicted to be class 0, which is hyperplasia. As you see, each one is accumulating to the previous one. This is another example where both red and blue exist. As you see, there is the base value, and if you return to the previous figure, it's a similar value because we mentioned that the base value is the average. So this contributes with 0, this contributes with a positive, this another positive, this a third positive, and this a negative. By accumulating all of that, we have a value of 1. It's not necessary to be exactly 1. It can be 0.9 or 1.1, but if it's above the average, then it will be predicted to be the other class, which is true by normal and predicted to be normal. There a third example, but on the experiment of all features. As you see here, we have the base value, this predicting or contributing to be positive, positive, negative, and positive, and the accumulation of those will be here 0.743 above the base value, and hence it's predicted to be the positive class or normal here and normal here. And you need to ensure that the true label and predicted label are correct so that you can interpret your figure. Now let's move to the second type of SHAP diagrams, which is called scatter plot, and you can plot it using the scatter function, and it accepts the different SHAP values. And here we are passing the whole instances with the top 5 features, and from that we can conclude that the scatter plot is for global explanations, and the scatter plot visualizes the relationship between the feature's value and its SHAP value across all instances in the test set. So simply, waterfall plot is local explanation and scatter plot is belonging to the global explanations. And let's know how to read. So let's focus on the last subplot. Here we have the sum feature on the x-axis and the SHAP value on the y-axis. As you see, in the x-axis, the values ranges from negative 2.5 to 2.5, and the SHAP values on the y-axis ranges from negative 0.8 to positive 0.4. And here, as you see in this plot, it's a scatter plot, point for each instance, and it's colored according to the corresponding SHAP value. And the trending here is it takes an upward slope from the left to the right, which mean a negative slope. This means that by increasing the sum value, the SHAP value or the corresponding SHAP value increases. And this implies that higher values of the feature are associated with a greater positive impact on the prediction. Again, the red color is associated with positive or negative SHAP contributions, but its high feature value, and the blue represents low feature values and is also associated with positive or negative SHAP contribution, and the colors between them is the range from the different SHAP values or the range of the SHAP values for a certain feature. There is another figure. As you see, there is a negative slope here. It decreases from the right to the left in the direction, the same here. And this means that by increasing the value of the feature, the corresponding SHAP value decreases, or by decreasing the value of the feature, the SHAP value increases. And this is the opposite. By increasing, the SHAP increases. And as you see here, there is two trends. One is negative and another is positive, so that you can interpret the plotted instances, and all of them refer to class 0, which refers to hyperplasia. The third plot is called summary plot, and it accepts also the whole instances, as you see here, and the top 5 features. And the summary plot combines the feature importance with the feature effects, showing both the magnitude of the impact via SHAP values, as you see on the x-axis, and the distribution of these effects across all instances, as you see here. So here on the y-axis, the features are ranked by their importance from the top to the bottom, and the x-axis, as mentioned, it contains the different SHAP values, and each point here corresponds to an instance, and the color encodes the value of the feature, whether it's high or low, and here are the intermediate values, and we can understand which features are most influential overall and how they affect the predictions. So as you see, we are dealing with the first order features. For the feature frequency count, as you see, there is low impact here across these features because most of them are blue in the low range, while for the sum, the opposite, there are high values here reflected by the high range or the encoding of these colors. So we can say that for the sum feature, by increasing the SHAP value, the importance or the influence of the sum feature is higher, while for the frequency count, it's the opposite. By increasing the SHAP value, the importance of this feature decreases. The last plot, but not the least, is the force plot, and it's plotted for an instance. So you define here the instance index and the number of features. So here we are dealing with top 5 features. So we can say that the force plot is categorized as local explanation, and here the force plot provides a detailed explanation of a single prediction by showing how each feature contributes to pushing the prediction from the base value or the average prediction to the final output. Again, features contributing positively are shown in red, while those contributing negatively are in blue. And first plot here are excellent for explaining individual predictions in a human interpretable way. So let's say this example also for the first order features. We have here a normal case, and this is our base value. So the sum, which is this value, pushes the contribution positively. The frequency count also pushes positively, but the count and the sum pushes negatively. So the whole values here is summarized by 1 if of x equals 1, and we can say it's label 1 because it's above the base value, so it belongs to the normal because you are encoding the normal to be 1 and hyperplasia to be 0. Another example, all of the features are pushing towards the negative or the lower range from the base value, so we are behind the base value, so it will be encoded as index 0, refers to the hyperplasia, and these are the different contributions of each feature. By summing all of them, you will reach to that value, which is 0. So simply, we have multiple plots, such as force plot, waterfall plot, and both of them are for local explanation. And the local explanation here refers to getting the contribution based on a specific instance, while scatter plot and summary plot are for the global explanations, where we are getting the trends of the different features along the whole instances. By combining all of them together, we can interpret the system alongside the high performance that we got. So in this lecture, we have introduced the meaning of explainability and why we should explain our model, and getting high performance is not enough. Also, we introduced the SHAP and the theory behind it, which is the Shapley value, and we introduced an example of how to calculate the Shapley value. Then we introduced how to do so using the SHAP package in Python and applied that on our project, which was introduced in the previous lecture regarding the Adriel Menis 3D dataset. We differentiated between local explanations and global explanations and introduced multiple figures and plots such as summary plot and scatter plot.